Okay, so today we're going to talk about the fundamental theorem of calculus, part 2. So this is the second piece to the fundamental theorem of calculus. We're still on that same theorem, but now for part 2, it says let f be continuous on the interval ab. Then the integral from a to b of f of x dx is equal to capital F of b minus f of a, which is basically just that evaluation theorem all over again. And this is where f is any antiderivative, so that if we take the derivative of capital F of x, we get lowercase f. So we come back to our original function. So this isn't really anything new. We've been doing this for a while now, evaluating definite integrals. And so now we're just putting it into this theorem. Now, most textbooks actually have this piece as part 1, but for our textbook, they have it as part 2. So just to keep it consistent, this is part 2 in our textbook. But if you do look at other textbooks, or if you look up the fundamental theorem of calculus on the internet, or sometimes this might be part 1, and the one we did on the last video will probably end up being part 2. But the important thing is that the fundamental theorem of calculus has these two pieces. So let's go ahead and do an example. Actually be a good idea for you to try this example on your own. So go ahead and pause the video, and then I'll do it with you in just 1 second. But since we've kind of been doing this, this is just really the evaluation theorem. Go ahead and try this on your own. Okay. So here we want to integrate the integral from -2 to 2 of t squared minus 4 dt. And so here I'm integrating with respect to t, and I have my variable t here, so I can just integrate like normal, take that antiderivative. And so if I take the antiderivative of t squared, that's going to be t cubed, doing that power rule, divided by 3. And then the antiderivative of a constant is that constant times that respective variable. So it's going to be 4t. And the limits, the bounds are from -2 to 2. Okay, perfect. And so now all I have to do is do f of b minus f of a. So here, this part here is basically our capital F of t, and this was our lowercase t. And so now our job is to do f of 2 minus f of -2. And so, like I said, nothing really new here. We've been doing this, and hopefully you're already really comfortable with this. And so just plugging into that function, we're going to get 2 cubed over 3 minus 4 times 2 minus, and then I like to put parentheses to make sure I don't mess anything up. It's going to be -2 cubed over 3 minus 4 times -2. Okay, and now if we evaluate this, we'll get 8 over 3 minus 8 minus -8 over 3 plus 8. Okay, and so then now if we evaluate this here, we should be able to get 16, yes, 16 over 3 minus 16, which is the same thing as -32 over 3. So hopefully you got this as well. And if you didn't, we need to practice some more. And so this is basically it for the fundamental theorem of calculus. I'm not going to do more examples of this because we've been doing it. It's just the evaluation theorem over and over again. But I will add a note for the fundamental theorem of calculus. So let's go ahead and do that. So a note on, and we just call it FTC for short because nobody wants to write that over and over again. So this is called, so what the fundamental theorem of calculus does is this theorem brings together differentiation and integration as an inverse process. Okay, so what this is saying is that basically what the fundamental theorem of calculus does is we know how to differentiate and we know how to integrate. And so what the fundamental theorem of calculus does is it shows us that if we integrate and then we take the derivative, we'll just get back that integration piece from the middle of that integral. So for part 1, it says that if you take, and we used f of t there, if you take f of t, that integration part in the middle, and we integrate to obtain g of x, then we can differentiate to obtain lowercase f of x, right? So we learned that basically for that first part, we really just swapped these pieces out. But we did it the long way where we had our f of t, and then we integrated to obtain our g of x, and then we differentiated that to show that we really just get f of x. So that's that inverse process they're talking about. And for part 2, if you take capital F of x, so remember that we notated the antiderivative in 4.7 by capital F, and so we can still do that. Then if we differentiate this, we get lowercase f of x. And then we can integrate to obtain capital F of x evaluated from B to A. Okay, so that's all that FTC is doing. This is kind of like a little summary of it. And so this is where I'm going to stop. You just really need to know the differences there for those. Okay, so now what we're going to talk about is we're going to talk about an average value of a function. If you have a function, they want to know what the average value of that function is going to be. And so the best way to kind of recall or to go about this is to recall how to find the average of something. So to find the average of a set of numbers, so to get the average of a set, basically what you would do is you would do the average, and I'm just going to say AVE for average, is that you would add all those numbers together, say we call them y1, y2, all the way to all the numbers that you have, which is y sub n. And to get the average of all of these, then you add all those numbers up, and then you divide by the number of elements that you have, right? Just like if I were to find the average of your test scores, I would take all your test scores, add them all up, and then divide by the number of students that I have. So same concept here. So in order to find the average value of a function, we actually have a little theorem for this. So we have the average value of a function. And this isn't too bad. It's basically just doing the fundamental theorem of calculus again, part 2, and just adding a little piece to it. So you're just evaluating a definite integral. So the average value of a function, so we'll just call it f of x, on the interval a to b is going to be, we'll call it f of for average, and we're going to do 1 minus b over a from the integral of a to b of f of x dx. So what you're really doing here is you are basically evaluating the integral from a to b of f of x dx to get the area under the curve between a and b. And then what you're really doing here for this part that says 1 over b minus a is you're actually dividing by the distance of from b to a. So if I have a function that's from a to b, right? This is my value b. What you're doing is dividing by this distance here, like how long from b to a am I, so that you can get the average of that function. So that's all there is really to it. So let's do a little example to find the average value of f of x when it equals 8 minus 2x on 0 to 4. And then we're going to do something a little bit different and then find c such that f of c equals the average value of the function. So here they want us to get the average value of this line, 8 minus 2x. So if we wanted to get the average value of this line, what we're going to do is we need to apply this theorem here, which means that we're going to be doing 1 over b minus a. In this case, this is my a value and this is my b value. So this is going to be 4 minus 0, just following this theorem here. And then I'm going to integrate from 0 to 4 of f of x, and my f of x here is 8 minus 2x times, 8 minus 2x dx, because we need to state what we're integrating with respect to. Okay, so the first thing we need to do is find the average value of the function, and then I'll show you how to find that value c so that our function is equal to the average value. Okay, so now we can simplify this a little bit more. This one's nice because we'll just get 1 over 4. And now we need to integrate from 0 to 4 of 8 minus 2x dx. And then this just becomes an integration problem. And we'll get 1 over 4. And then if we integrate 8 minus 2x, the antiderivative of a constant is just 8 times the respective variable here, which is x. And then here we'll get negative 2x squared, and then divide by 2, which would cause that to be just x squared. And we're going to evaluate this from 0 to 4. Okay, and so now what we need to do is for this piece, we're going to apply the fundamental theorem of calculus part 2, or the evaluation theorem. And we will get 1 over 4 times 8 times 4 minus 4 squared minus 8 times 0 minus 0 squared. Now I'm just showing all my work here. In reality, if you know this part's going to zero out, then you don't really need to do it. Okay, so here we have 1 over 4 times 32 minus 16. Which gives us 1 over 4 times 16, which is equal to 4. So here, this is our average value. So our f_av, which I probably should have put here, is equal to f_av. Okay, and now our second job is to find the c such that f of c equals the average value of a function. Let me turn that page and go here. So we know that our f average is equal to 4. And we need to find a value c such that f of c equals f_av. Well, f of x was 8 minus 2x, right? So f of c is just 8 minus 2c. But we need this to equal f_av, which is equal to 4. So in order to find that c value, all you'll do is do 8 minus 2c is equal to 4 to find that c value. Pretty easy now, it just becomes a basic algebra problem. So what you'll do now is just solve for c, move 8 over to the other side, and then you'll get negative 2c minus 4. And divide by c on both sides, and so you get c is equal to 2. So this here is the value c that gives you value c such that you get the average value of the function. Okay. And now what I want you to do is I want you to try one, and I'll give you the answer, but I won't go over it, but you should try it on your own just to get some practice. So you try doing, given that the integral from 0 to 3 x squared dx is equal to 9, you want to find c such that f of c equals the average value of f of x, which is equal to x squared, on 0 to 2. So actually, I do want to go over this a little bit. So here what they want you to do is they want you to find c such that it equals the average value of the function. Here what they gave you was the integral from 0 to 3x squared dx, which equals 9. Now you could have easily figured that out by, integrating, wait, this should be on 0 to 3. You could have easily found that out by integrating, finding the average value here. But, they made your life a little bit easier, so you didn't have to do that. So here they didn't give you the average value, they just gave you the integral. But remember that the average value means that you have to have 1 over b minus a to get the average of that function. So the first thing is you need to find f_av. So you need to do f_av, which equals 1 over b minus a, which is 1 over 3 minus 0 times the integral from 0 to 3x squared dx. Nice thing is they already gave you this and they told you this equals 9. And now you have that 1 over 3 in the front. So this is the same thing as 1 over 3 times 9, which is just 3. So this is your average value. And now all you have to do is find your c value and do f of c is equal to c. So then you'll get c squared is equal to 9. So if you take the square root of both sides, you'll get that c is equal to plus or minus 3. Now here we have to be careful because we have two c values. We have 3 and a negative 3. But our interval was 0 to 3, so that means that we can't take this negative 3. Our average value is going to be c is equal to just 3. Okay, because it needs to fall in our interval of where we're taking that average. Okay, everybody, so now we're going to talk about the mean value theorem for integrals. So we did skip the mean value theorem in general for the derivatives, and that was just because you don't need it too much for Calc 2, and the coordinator for this class actually recommended that we skip it so that we don't fall behind because of this craziness going on. So, but the good thing is that you don't really need to know the mean value theorem for derivatives in order to be able to use the mean value theorem for integrals. Because the mean value theorem for integrals is just kind of an extension of that average value theorem that we did earlier. So what the mean value theorem says that if f is a continuous function on AB, then there exists a number c in AB such that f of c is equal to the average value, which is basically what we did earlier, but now we can use it this way where we do this instead, okay? So instead of, finding the average value and instead of finding the average value and then plugging in c into our function and then setting it equal to the average value, we could then apply this, which is really just a backwards way of doing what we did here, where we found the average value and then we found the value for c. Now, what we do here is it's basically the same thing, because if you think about it, when we finally find the c value that gives us that average value, what we did is first we found f_av. And then we computed, and after we computed this, we set this equal to f of c. Well, this here, it's basically the same thing, but instead of having 1 over b minus a, we basically multiplied f of c over to both sides. What I mean by that is, maybe if I show you, this is the formula that they give you, but what this really is we do f of c is equal to this, right? But if I multiply it by b minus a over on both sides, I really just get b minus a times f of c is equal to the integral of a to b of f of x dx, which is the formula for that mean value theorem. Super easy. It's basically all you've been doing it, now you're going to do it in a different method. So let me And it's really not even that different. It just looks different. You've already been doing this, but now you have a whole little formula for it. Okay, so let's do a quick example. So an example here is determine the number C that satisfies the, I'm going to call it the mean value theorem for integrals. So I'm going to say MVT, or integrals, for the function f of x is equal to, let's do a quadratic, f of x is equal to x squared plus 3x plus 2 on the interval 1 through 4. Okay. So what we want to do here is we want to apply the theorem that we have up there, and we want to find that C value like we did earlier. But what we're going to do is, since we're applying MVT, or the mean value theorem for integrals, we're going to be using this formula. So if we do the integral of f of x dx, that's the integral from 1 to 4. F of x is equal to x squared plus 3x plus 2, and don't forget your dx. And we're going to set that equal to f of c. Now, if this is our f of x function, then f of c is just going to be c squared plus 3c plus 2. Nothing crazy, we just plugged in c instead of x because of this part here. And now we're going to do times b minus a, which is 4 minus 1. So all I'm doing here is I'm showing you what happened. So this part here is the integral from a to b of f of x dx, and then we set that equal to, this part here is just f of c, and this part here is just that b minus a. So I'm just plugging that into that formula, and that's it. And now I could evaluate, because I know how to evaluate a definite integral, and you should too already. So now let's do the left-hand side. So to evaluate that definite integral, we would do that backwards power rule. So the antiderivative of x squared is x cubed over 3 plus 3 times x squared over 2 plus 2x plus 2x from 1 to 4. And we're going to set that equal to 4 minus 1 is 3. So I'm just going to go ahead and now just distribute that 3 into the our f of c here, just to make that easier for us. So it's going to be 3c squared plus 9c plus 6. Okay, and so I'm going to move this over to the next page so that we have room. Okay, and so now what I'm going to do here is I'm going to evaluate my left-hand side for my upper bound. So remember, to evaluate this, it's just f of b minus f of a, using the fundamental theorem of calculus part 2, which is the same thing as doing f of 4 minus f of 1. So that's what we're going to go ahead and do. So that's going to be 4 cubed over 3 plus 3 times 4 squared over 2 plus 2 times 4 minus 1 over 3 plus 3 over 2 plus 2, and this is all equal to that right-hand side, which is 3c squared plus 9c plus 6. Okay, and now we're simply going to evaluate this part here and this part here. So this is going to be, I did it ahead of time, is 160 over 3 minus 23 over 6, which is still equal to this right-hand side, 3c squared plus 9c plus 6. Okay, now if we simplify this left-hand side, we're going to get 99 over 6, which is equal to 3c squared plus 9c plus 6. Now our goal here is to get c by itself, because we want to know that average value for c. So what we're going to do is, this is a quadratic, so to get a c value for this, maybe we can factor or apply that quadratic formula. But we can't do that until we set this side equal to 0, right? So I'm going to move the 99 over to the next, to the right-hand side here, And so I'm going to do that on the next page just because I don't know why I'm writing so huge. Okay, so if we move that over to the right-hand side, we're going to get 0 is equal to 3c squared plus 9c minus 87 over 2. Now, I don't think that this is going to factor. We can, if we want to, multiply everything by 2 to get a common denominator. And we can just now apply that quadratic formula. So if you do, you can apply the quadratic formula from here, or you can go ahead and first multiply by 2 to get rid of that fraction. And actually, we could have done it earlier. I don't know why I didn't do it earlier. And get, if I multiply everything by 2 to get rid of this here, it's going to be it's going to be 6c squared plus 18c minus 87. Okay, and so now after this, we can just plug that into the quadratic formula. But I went ahead and did it because I didn't want to spend lecture time doing it. So when you apply the quadratic formula and you simplify it all the way down, you will get c is equal to -3 plus or minus the square root of 67 all over 2. So this is as simple as it gets. Now, you could leave it like this, right? But we have to be quite careful with this, because what if one of the values is out of the bounds? So what you want to do here is recall that you were doing the average value or doing the mean value theorem from 1 to 4. So let's go back and write that our interval was 1 through 4 so that we keep that in mind. So, I mean, although I do like for you to leave it in this exact form, I still would be a great idea for you to actually put this in your calculator and see what this is actually equal to. So if you do -3 plus the square root of 67 over 2 and -3 minus the square root of 67 over 2. So these values are actually 2.593 and -5.593. Now, what we're actually looking for is to make sure that none of these are outside the bounds, because if they are, then we need to take those away and just take the one that it is, kind of like the one we did earlier. So our bounds are between 1 and 4. So looks like this one's in between those values, but this one's not. So we could go ahead and throw it away. So the C value that works with this is 2.593. Okay, and that's it. And so this is it for 5.4. Actually, it's not that bad. The newest thing of all is obviously finding that C value, but it's really not that hard. Most of the concepts are coming from algebra. And then the fundamental theorem of calculus part 1, I think, is a little trippy sometimes, but it's not too bad. Just do a couple of those homework problems and you should be okay. So we're going to do 5.5, and that's the last section in chapter 5. And then after that, we just have 7.1, and then that's it. And then that's Calc 1 for you.